Welcome to The Explainer. Today, we're going to talk about how one single idea triggered this massive domino effect all across the world of AI. It's a concept that started with understanding language, but then it learned to see, it learned to hear, and now it's probably powering an app on your phone. So let's trace the path of that very first domino.
Right. Our story kicks off in 2017 with this paper. And that title, Attention is All You Need, it wasn't just catchy, it was a bold declaration. A team of researchers basically said, hey, what if you only need one mechanism called attention to build world-class AI for language? Well, turns out they were right, and it started a revolution.
So, what was so revolutionary about it?
Well, the paper introduced the transformer. And this new architecture, it was built to solve a really specific problem that computers had been wrestling with for years, something called sequence transduction.
Now, sequence transduction sounds super technical, I know, but you actually see it all the time. Think about it. Translating a sentence from English to German, that's a perfect example. You're just transforming one sequence of words into another sequence of words. That's the exact task the transformer was designed to nail. You see, before 2017, the best models were these complex beasts. They were built on things called RNNs and CNNs, and they had to process information one little piece at a time, in order. It was slow, and it made them a real pain to train. The transformer's big, radical idea was to just throw all of that out. It relied only on attention, which could look at all the data at once. This made it way, way faster and more efficient. And the results? They were immediate. This number, 28.4 Bleu, that's its score on a standard test for translation quality. And not only was this a huge jump over the old record, but the transformer did it using way less training time. So it was simpler, it was faster, and it was better. The first domino had just fallen.
Okay, so with language basically conquered, this new question started popping up everywhere. If this architecture is so good with sequences of words, could it handle other kinds of sequences? You know, like the sequence of pixels that makes up a picture.
And this was a huge question. I mean, for years, computer vision was the undisputed territory of convolutional neural networks. They're literally designed to find patterns in images. So could this new kid on the block, this language model, even hope to compete? Well, the answer came in 2020 with another paper that had a brilliantly clever title. It introduced the vision transformer, or VITE for short. And the title, it kind of gives away the whole trick. The big idea was to treat an image not as one big thing, but as a sentence made up of image words. The concept was just so elegant and simple. Instead of building a whole new system from scratch, they just adapted the original idea. You take an image, you chop it up into a grid of smaller patches, and then you just treat that grid like it's a sentence. This sequence of image words gets fed straight into a standard transformer. And the result? It was shockingly good. It matched the performance of these giant specialized vision models, but often needed way less computing power to train. And just like that, the vision domino toppled over.
Okay, so transformers can read, and now they can see. What's the next logical step? Well, can they watch? Video is really just a sequence of images, but with this extra dimension of time thrown in. And that was the next big challenge.
And wouldn't you know it, pretty soon another paper shows up with a playfully familiar title. This one introduced the Timesformer, a model specifically designed to adapt the transformer to understand video.
The real trick with video is handling time. How do you process what's happening from one frame to the next? The Timesformer just tackled this head-on. It learned to pay attention not just to the different parts of a single picture, but to how those parts changed and moved across the whole video. It was understanding space and time together, without needing the clunky 3D models that were used before.
And the advantages over the old methods were massive. Compared to the big 3D video models, Timesformer was way faster to train and much more efficient to run. It could even analyze video clips that were over a minute long, something older models really struggled with. So it's no surprise it set new state-of-the-art records for things like identifying actions in videos. Down went the video domino.
Text, images, video. You can probably see the pattern forming here. The next frontier was another one of our senses, audio. And just like with vision, the world of audio processing was dominated by its own kind of specialized models. So, was it time for another disruption?
You bet it was. The audio spectrogram transformer, or AST, soon came onto the scene. And it asked the exact same question that the vision guys did, but for sound. It was like, hey, are we sure we really need all these specialized models for audio?
And they followed the exact same playbook. AST took the pure transformer architecture and applied it directly to sound. They take a spectrogram, which is basically just a picture of a sound, chop it into patches, and treat it just like the vision transformer treated an image. It was this brilliantly simple idea crossing over from one field to another. And it worked perfectly. Across all the major audio challenges, for environmental sounds, for speech commands, for general audio events, the AST just set new records, a new state of the art. It proved, once again, that attention alone was powerful enough to understand sound. And with that, the fourth domino fell. Okay, so at this point, the transformer seems completely unstoppable, right? But there was a catch. These pure transformer models, they were incredibly powerful, but they were also huge, and they burned through a ton of computing power. So the next big challenge wasn't just about raw performance anymore. It was about efficiency. How do you make these things small and fast enough to run on, say, your phone? This led to a really clever new idea. What if, instead of choosing one architecture over the other, you could combine the best of both? You know, CNNs are really lightweight, and they're great at seeing small, local details. And transformers, well, they're the heavyweights, but they're unmatched at seeing the big global picture. So why not build a hybrid? And this best of both worlds approach gave us a whole new family of models, like MobileV for images and FAST for audio. The idea is that they use efficient little CNNs to do the initial work, to process all the fine-grained local stuff. And then they feed that information to a transformer to figure out the bigger context. The result is something that's both really powerful and really lightweight. And the results were fantastic. Just look at MobileVit, the hybrid model. On this standard image benchmark, it was over 3% more accurate than one of the leading mobile-focused models while being about the same size. You're getting more power for the same computational price. Now, the same thing worked wonders for audio. A hybrid model called FAST got top-tier performance while using up to 150 times fewer parameters or components than the models that came before it. I mean, that's not just an improvement. That is a gigantic leap in efficiency. So there you have it. From one powerful idea in a single paper back in 2017, we've watched the transformer architecture completely reshape entire fields of AI, one domino at a time. It learned to read, then see, then watch, and then listen. And finally, it learned to be efficient enough to live in our pockets. Which leaves just one question. What domino is going to fall next?